In this video, we'll explore an electrical phenomenon known as voltage drop. Simply put, a voltage drop is the loss of voltage that happens when current flows through circuit components that feature a certain resistance. When a significant voltage drop occurs where it shouldn't, the device ends up receiving less voltage than it needs. As a result, it may malfunction or operate below its full potential. Let's take a closer look. Consider a simple circuit powered by a 12-volt source. Let's assume the only resistance in the circuit comes from the bulb, while the rest of the circuit has no resistance at all. In a healthy circuit, the voltage measured across the bulb will be 12 volts, and the bulb will shine at full brightness. In other words, the voltage drop across the bulb is 12 volts. You might be wondering why this phenomenon is referred to as voltage drop. Let's clarify with a practical multimeter test. Place one probe on the battery's positive terminal and the other on the bulb's negative terminal. The multimeter reads 12 volts. Now, move the probe from the negative terminal to the bulb's positive terminal. This time, the reading is 0 volts, confirming a 12 volts voltage drop across the bulb. Now let's take a look at a similar circuit featuring two bulbs. If both bulbs have the same resistance, the voltage across each will amount to 6 volts. In other words, the voltage drop across each bulb will be 6 volts. The bulbs will no longer shine brightly since they are sharing the available voltage. If bulbs have different resistance values, they will receive different voltages. The voltage division rule states that voltage across components divides directly proportional to their resistance. Let's say one bulb has a resistance of 4 ohms and the other 2 ohms. Now we'll calculate the voltage drop across each bulb. For this, we'll use Ohm's law. We multiply each bulb's resistance by the total circuit current. Here the circuit current is 2 amperes. This means that one bulb will get 8 volts, while the other will receive 4 volts. In other words, the voltage drop is 8 volts across one bulb and 4 volts across the other. If we measure voltage across the bulbs, the multimeter will return the same values. Let's take another measurement to clearly see the voltage drop after each bulb. At point 1, we have 12 volts. At point 2, 8 volts. The voltage drop across the first bulb is 4 volts as expected. The voltage drop between points 3 and 4 is 8 volts. Let's return to our single bulb circuit and consider what happens when a fault develops. Examples of common faults include corroded contacts, damaged wiring, poor connections in a connector, a bad ground. Any of these issues can result in unwanted resistance in the circuit. As you may remember, voltage distributes across components in proportion to their resistance. Let's say a faulty connector has developed significant resistance, 1 ohm, while the bulb's resistance is 3 ohms. The current in this circuit is 3 amperes. As in the previous example, voltage will now divide between these two components based on their resistance. The bulb receives 9 volts, and the faulty connector receives 3 volts. Therefore, the voltage drop across the bulb amounts to 9 volts, while the voltage drop across the connector is 3 volts. Thus, 3 volts are lost in the circuit due to the connector fault. The bulb only receives 9 volts and, as a result, glows dimly, operating below its full capacity. It's essential to understand that voltage doesn't simply vanish. It redistributes throughout the circuit and still performs work. However, in a faulty connector, that work is no longer useful. Instead, it manifests as heat at the point of resistance. Simply put, the connector has effectively become a load, acting as a heater now. Any other component in a circuit can similarly turn into an unintended load when its resistance increases due to a fault. In an ideal circuit, all of the source voltage reaches the load. In reality, however, every element including wires, connections, and contacts has resistance, even when they are perfectly healthy. To have minimal impact on the device's operation, in this case the bulb, the resistance should be very low, close to zero. As a result, when current flows through circuit components, a small voltage drop occurs across each one, even across perfectly healthy wires. Let's measure the voltage drop across each element in our example circuit. Keep in mind that voltage drop must always be measured on a live, loaded circuit. Otherwise, the readings will be lower than the actual values, thus concealing the problem. If a section of the circuit is shared by multiple loads, it's recommended to turn on all of those loads when measuring. Even our simple example includes such shared sections, the ground wire and the body, both used by many devices. For this reason, when measuring voltage drop on the ground side, you should turn on other high-powered devices connected to the ground. As you can see from the measurements, a voltage drop occurs across every element in the circuit. We can also measure the voltage drop across an entire side of the circuit. Let's start with the negative side. Now let's measure the voltage drop on the positive side. All of these readings are within acceptable limits and will not significantly affect device operation. There is no universal standard for acceptable voltage drop values. However, the table on the screen shows typical voltage drop limits in a 12-volt automotive system. As a general rule, the total voltage drop in any single circuit should not exceed 3%. For circuits with high power loads, such as in the starter motor circuit, a slightly higher voltage drop may be acceptable. These values are provided for reference only. Exact acceptable limits for specific circuits may be specified by the manufacturer. Before wrapping up, it's worth noting that measuring component resistance is not a reliable way of detecting voltage drop issues. A component may test fine, but its resistance can increase significantly under load, resulting in a substantial voltage drop. Thank you for watching.